Should you start? Yeah.
Hey guys, this is James, Shreya, and Baba, and we'll be going through the second assignment for artificial intelligence. So this week, your assignment is based on search, and we'll just go through the assignment details and give you a brief overview of what needs to be done this week. So these slides are based on the previous TA's presentations, which were Trace and Mukundan. So this assignment is already out and the grade scope is live, and the due date is on Feb 9th, and that's at 11:59 anywhere on earth. And you have unlimited submissions for this assignment, but you can only make 2 submissions every 30 minutes. So that's about the administration. So how do you start? So you just need to go and git clone your assignment to, and please note that you always clone from the master branch and activate your AI environment which you created in assignment 0, and you should be good to go. So about the project code structure, let's just go through the assignment repository. So this repository has a bunch of resources that you can use, and we recommend you to go through all of these because this will give you a better idea on how to approach the problem and the assignment, of course. And there are a bunch of test cases and files. So the submission.py is the file that you should be working on, and this is the file that you submit eventually. So the test cases are your search submission test, search unit test, and search submission test grid.py. The search unit tests, they are a very detailed test which check your algorithms very deeply, and it checks all possible pathways. Your search submission test.py is basically used for your visualization purposes. So it basically only checks one single path, and it will help you visualize your start and your goal and what's the path taken.
And also the nodes that you explored to get the path.
Okay.
And then later, then you also have some files related to the Romania map, the Atlanta map. So you can test on both the maps. Like for the grading purposes, for the assignment, we would be using the Romania map.
And Romania map is smaller.
Yeah, it's a smaller one. Atlanta map is pretty huge. And then these are like some of the helper classes that we used for the assignment then.
Okay.
And yeah, then we start off.
And these are a bunch of resources, and we recommend you to go through all of them because I'm sure that these are all applicable in your assignment. And we also insist please go through the FAQs because these will answer most of the questions that you have, and also go through the FAQs which are present on the Piazza post. Because those basically concentrate or emphasize on the frequently on the errors that you frequently get, and we have addressed all of them, so we recommend you to do that. So we start off this assignment with a few warm-ups. So first we will have the implementation of the priority queue. So this is a first in and first out queue, and I'll just go through the submission.py where you'll need to implement it.
So in this one, like we expect you to fill in the pop and the append method. Like you can make use of the heap queue methods like heap push and heap pop, like for implementing these methods. But just keep in mind that we need to ensure the FIFO property, so you might need to do some small change regarding that. There is also a remove method, which is not compulsory. You may choose to use it in certain cases depending on how you choose to implement your later algorithms. So we leave it up to you. And finally, we would say that priority queue is something that is a very small aspect of the assignment. So please don't spend a lot of time on it. We have seen in the past students spend like at least a couple of days or so. It's not worth the time, at least for this assignment. So please don't do that.
So your next warm up would be your breadth first search, so or the BFS. So you are given three parameters or arguments, which is your start, your goal, and the graph on which you will be utilizing. So note that the graph, the BFS does not account for the costs within each of the edges. So it just radially searches through the graph without any heuristic. And yeah, and make sure that so two things to note in this is that the terminating condition for BFS is different, and we have also provided a link in the resources, a video, I guess, which explains why it's different. And also make sure that while you're adding uh, the nodes to the frontier, it should be in the alphabetical order. And the why we need this is because of the unit edges, because we don't know which edges are there. It's easier for us to check when it's alphabetically
It will
ordered.
basically help us have a consistent solution for all the different for all the test cases that we have, just so that like all of you get the same answer, and it will help in the grading part there. So please follow that. Then next is uniform cost search. This is kind of similar to BFS, just that a very simple difference being that you incorporate the weights of the edges that you have. Again, now the terminating condition for UCS would be different from BFS, so keep an eye on that. And like if you want to think of UCS, you can think of something as like from the start node you are expanding radially outwards, so you're kind of forming a circle towards the goal, and whenever the goal gets within the circle, then you have found it. So yeah, that's how you can imagine a UCS flow being. And yeah, coming over to the last of the warm-ups, this is A star.
So, okay. In A star, this is a much more efficient search algorithm. So, why is it so? Because it uses a heuristic, and heuristic is basically a good guess that you make in finding the distances between the nodes, and this helps in reducing the number of nodes that you have actually explored. And you have to, in case of A star, I think the most basic heuristic that one can use is the Euclidean distance heuristic, and we ask you to finish up this function so that you can make use of that inside the A star function. So next is the bidirectional UCS. So unlike the traditional UCS where you have a search and a goal, so in this you search from both the start node as well as the goal node, and this is a much more efficient search because the terminating condition ends when the two searches intersect in the middle. And also you can note that in the UCS there is one huge subgraph. Sorry for the disturbance. Yeah, so in traditional UCS there is a one huge subgraph which explores all the possible nodes, but in case of bidirectional UCS there are two subgraphs which start exploring, one from the start and one from the goal, and when they intersect, that's when the search terminates, and hence it's a much better efficient algorithm. And yeah, so that's pretty much it of bidirectional UCS. And similarly, we have the bidirectional A star itself. It's essentially almost same, but except that you have a heuristic.
Is that like so basically rather than expanding radially, you tend to expand towards the other goal that you have. Again, the terminating condition for this would be pretty similar to what you had for bidirectional UCS. So if you're done with bidirectional UCS, you should be able to finish a bidirectional A star pretty easily. So yeah, it's something that you can do. Then coming on to the tridirectional search, this is like one of the advanced topics that we have for this assignment. It is also a research problem that Thad has been exploring with some of his students. So that's why he is pretty interested in it. In this case, what you are essentially doing is in bidirectional we expanded to from two nodes towards each other. In this case, we are expanding from three nodes and trying to find a path connecting all the three nodes. So if you have nodes given ABC, you can return either path from A to B to C or A to C to B, whichever is the most efficient path that you find, you can return that. So again, as an idea, in this case, from each of the nodes you try to expand towards the other two nodes. So if you're starting from node A, you would try to expand towards node B and C. Similarly, for from node B, you would try to expand towards node A and C. And whenever you encounter any intersection, then you have found the shortest path connecting those two nodes. Then you need to look at, like in some of the cases, finding two of the paths would give you the most efficient path, or in some cases you would need to look at the third path. So yeah, we would recommend you to go through the resources and see in what cases you are good with the two paths, or in what cases you need to look at the three paths. So yeah, that is. And then finally you have the tri-directional upgraded. In this one we have asked, like we have provided some alternatives that you can use. Like one is basically tri-directional A star, or you can use landmark search. But most of the times we have seen people using tri-directional A star, since it is a straightforward conversion of your tri-directional UCS code. So yeah, again in this case you expand radially towards both the goal nodes. One thing that you might want to keep in mind is how you define your heuristic, and like how you make use of the heuristic. That is something that can help you a lot in solving this particular part of the assignment. And then you just return your name. Yeah, and then we also have the custom heuristic method. If you are not happy with the Euclidean distance method, you can use a custom heuristic. But yeah, but we can say that yeah, most all the test cases, like all the A star test cases, pass with the Euclidean distance. So you are not expected to do this, but if you want, you can do it. And then finally, the custom search method is for the race. So in the README you can see there is a small section about the race. We will put up more information about it sometime next week. For the race, we are expecting you to come up with a path between two nodes, not the tri-directional one, like not three goals. Here you will have just two goals. So you can, as a very basic way, you can simply use your bidirectional A star, or then you can come up with some other algorithms that we have provided as a hint. Like one thing is landmarks. So, and another thing to note is this race would be conducted over the Atlanta map. So, and yeah, that is about the race. Yeah, and these two methods are like load data is something that you can use for the landmarks computation. Yeah. Now, in the test files, you can go through the test files once.
Okay.
Just
There are a few of them.
yeah, go
This
on.
one? Okay.
So, just one. So for search submission tests, these are for the priority queue. In this case, we are basically trying to add 10 random numbers and remove them, and we just check that if the order that you are having it's correct or not. To be more sure of your answers, you can try to do this for a larger number. Say maybe try doing 1,000 numbers or 10,000 numbers to verify that your implementation is correct. Then similarly, we do the FIFO check. Then these are the BFS tests, UCS tests, the stars tests. So in this case, what it would do is, from a particular start to goal node, it would create the path and draw it based on, and you will get to see the start node, end node, what nodes you explored, what path you get. So that will help you with that. This will help you to visualize. Another file that we have is search unit tests. This is more of a comprehensive testing file. In this you can test all the paths possible. Like for the BFS test would basically, there is this test BFS Romania. It will go over all the possible start and goal nodes, and it will check if the path you are returning is correct or not. Similarly, there are UCS tests, A star tests. Again, running this file directly would create a lot of noise, especially when you are in the middle of implementing. So you would get some as not implemented, and so in the README we have provided a way to call individual methods. So you can probably use that, and that will reduce some of the noise for you. Yes, that is largely about the tests. Now we can go ahead.
So we just talked a bit about the local tests, and they are fairly comprehensive, but the purpose of them is largely for a sanity check. As with assignment one, we definitely encourage you to create your own tests to get more of those edge cases and to iron things out. Um, with Gradescope, you're going to be submitting that submission.py file that we just went over. Um, Can they do that? Yeah. When
You can look at the solution that you have submitted and download any of them. That's the feature that Gradescope gives you. Also, if you want to activate any of the older solutions, you can do that, like the solution with the best points that you have. And lastly, the time taken for your solution to be graded might vary a bit depending on how many people are submitting and how efficient or inefficient your solution is. So please bear that in mind. Yeah.
Okay.
And yeah, as always, start early. Gradescope and Piazza tend to get very busy towards the end of the assignment. So the earlier you start, the easily your doubts would be cleared. So yeah, please start early.
So questions. I see one question. Can we assume if we pass the local test, will we will definitely pass a grade score? I don't think so, because your local tests only check for your optimal paths and not for the number of explored nodes that you have done. So on Gradescope, we check for that part of the efficiency. So Gradescope essentially checks that your algorithm is efficient with respect to the number of nodes which are being explored. Can we use any other built-in methods such as queue or no?
I mean, yeah, like we would recommend you to use the heap queue library itself, which is pretty comprehensive and.
But priority queue has the test, right?
Yeah.
Okay.
So, but I mean, you can. Okay, no. Yeah, we would recommend you to stick to the heap queue and basically, just so that like it is being consistent with all the requirements that we have provided. Any other
questions on Piazza?
Yeah, let's. No, not here.
we already talked about that.
Can you go over the differences between different test files? Yes, we did. I think second question, no need. There is a Udacity video for explaining about the termination condition in BFS.
Yeah. So I think that should be it for the presentation.
Are there any questions on P and P?
Okay. There is another question. Can we track the parent-child relationship in a dictionary when looping through neighbors so we can find the path from goal to finish through tracking parent pointers? Yes, you can do that. So that is like one of the way you can do it, or you can also store the path in a way. But yeah, that is one way. But what you cannot do is store all the neighbors for a particular node. But yeah, you can store the immediate parent for that particular in the context of that particular search algorithm. You can store it.
I think we missed one question. Can we use internal heap queue functions that start with __? Yes,
You
I
can,
think
but
so.
you shouldn't need to.
You shouldn't need to. That's what we will say. And plus, I'm not sure because these would be private functions, so you probably won't be able to call them. But again, you shouldn't need to. Like the basic heap push function and heap pop function should suffice for all of for what all requirements we have. Do we have anything on?
Is that it?
Yeah.
Okay. Then good luck. We'll always be on Piazza to answer your questions. And please start early. Oh, we have one more.
Oh, we have one.
Can we use multiprocessing for async?
Or async.
No, all of your solutions would be run on a single processor. So, and again, like the idea of this assignment is not your parallel processing skills. It's more about the search algorithms. So, please don't spend your energy and effort doing that. Rather, focus on the algorithm aspect.
Okay. Okay. So bye. Good luck.